Okay, so at Norman's instigation, I drew a picture of the various data types we've been discussing, and Norman is even now uploading somewhere.
At the bottom.
The bottom of that. Oh, this whole list of contents here. Oh, I see. Yeah.
Oh,
wow. Isn't that wonderful? Generated instantly by Dot. Norman as driver. So we've this is a kind of what data types depend on which other, so it's a kind of useful roadmap. We've talked about rudder names here, which contain an OC name and modules, and there should be a line from module name to rudder name. We didn't have one here, right? Because the crawl ones are like that. And modules are module names, package IDs, OC names have namespaces. Names have an OC name and a. Oh, names have a module. We need a line here too. Modules and names. And then names, as I said, have the, so rudder names kind of expire after the renamer has got rid of rudder names. They have no further lifetime in the compiler, but names live on inside type constructors, classes, data constructors, and IDs and type variables. They live on throughout the whole of the rest of the compiler, which is why they're so pervasive. So I'm going to do a quick skirmish now with classes, data columns, and type constructors, trying not to get diverted for too long at a time. This picture, well, you will have access to this.
All those arrows mean the same thing. It's part of. Is that
They mean it's part of, yes.
What did that address?
The dotted arrows, they shouldn't really be dotted. This means the types mention classes and classes mention types. Right? So they mean there's a big loop. So in fact, the middle part of this stuff is a huge plate of spaghetti in which everything points to everything else. And so there's a few fix IOs happening in there to build the spaghetti. In fact, there's some well-advertised places in the compiler where you have to be a little careful. The word we've got two entities, right. So the business of the type checker, having got the rename of all these name things, the business of the type checker is to construct these the type version of the program. The key data types there that also live for a long time in the rest of the compiler are term variables and type variables, type constructors, data constructors, and classes. And they're described in this page. And I'm not going to just want to know about the existence of these data types and roughly what kind of things you look for there. So, but just before going into there's a straightforward sum of these four types, and that's what a type thing is. So the type environment, for example, that the type checker maintains is a mapping from name to type thing. Right, so given a name, it'll tell you, it'll say Fred is an ID, or it's a data column, or it's a type column. So that's the, rather than having four environments, we have one with four disjoints. So that's all the type things. Maybe we should call it an entity, but currently it's typing. Okay. So now, each of these four things, ID, data column, type column, and class, you should think of as a value. It's just a straightforward, immutable value, no mutability here anywhere. And it's just a record of all the things you might want to know about this thing. So, let me skip IDs at the moment and just do, what happened to type columns and classes? Maybe I didn't write anything about type columns and classes. So, a type constructor, for example, is just a big record of lots of information about was this an algebraic data type, or is it a tuple, or is it a new type, or is it a type synonym? And for each of those, so actually that's four different constructors. Each of those has a lot of information about, if it's an algebraic data type, it has a record, has information that gives the list of all its data constructors, for example, or its kind. Each of the data constructors will in turn contain the type of the data constructor, and that, of course, will mention the type constructor. So that's why data constructors mention types, which mention type constructors, which is why everything is in a plate of spaghetti. Okay. So these three, in a way, are somewhat self-describing. If you look, there's basic types datacon.lhs. I think tycon and class are both modules in the types directory, and they're fairly well documented, and they're all abstract, so that only tycon.lhs knows about the representation of tycons. Only class.LHS knows about representation of classes. And if you look in there, I think you'll see that the records in there are fairly well commented as well. So I'm not going to go through them just now, but take a look. And all of these things come with useful and fairly simple accessor functions, like ID type is a function from IDs to types. This is fairly common nomenclature. Type and then field name or what you want to select out of it. And this is no more than just a selector, just picks the type field out. And so you can tycon datacons will give you the data constructors for a particular tycon. And datacon tycon will give you the type constructor for that corresponds to the data constructor, and so forth. There's a whole bunch of these kind of functions, and they're completely non-stateful. They don't need environments to look up in. They're just lots of records, all of which point to each other. Term variables and type variables deserve a little bit more attention because one of the major design decisions in GXC at the moment is that these are the same data type. So ID and tyvar are both synonyms for var. And var here is allows you to make essentially dynamic distinctions between type variables and two different sorts of term variables. Now having one data type for all sorts of variables is very helpful for when, for example, finding the free variables of an expression. The free variables of an expression in the intermediate language can be type variables or term variables. You just get a single var set of var. If you have a lambda, which we do in the core intermediate language, it's just lambda var term, right? So rather than having two different kinds of lambda. So it's very, very convenient to have the same data type for both. Sometimes you have sets that you know are just type variables, and that's not statically reflected in the types in the compiler. But I'm quite satisfied with this compromise in the end. It worked really well. There's often a tension, I find, when writing big programs about how many static distinctions you make. I'm sure that many of you experience this. Okay, so in this page, I took trouble to write down quite a bit about what a global ID is and what a local ID is. And I think my suggestion would be just that you read that for now. We're going to come back to it if it's when it becomes relevant to any of you. But this distinction here took me some while to come up with, but it slowly solidified into a form that seems to work pretty well. Briefly, a global ID is an ID that comes from the outside of the module being compiled, and therefore is somehow immutable. It's not going to change its strictness or its arity. Nothing about it is going to change. Whereas a local ID is kind of defined somewhere in the module we're compiling, and as we repeatedly run the optimizer and so forth, it might change some of its properties, and so you need to be a bit more careful about looking it up in environments to make sure you've got the most up-to-date information for it. Also, if you're finding the free variables of an expression, we're usually interested just in local IDs, locally bound things, because the global ones are just like constants. We don't treat them as free variables. So, but there's quite a lot of notes further down in this same page that try to articulate the difference between global IDs and local IDs and how they're used and what properties that they have. Again, data types are a superb place to write these invariants down. What else to say? One other thing about global IDs is you'll see that there's a bit more information about what kind of global ID it is, and that's described just down here, where you'll see this is, again, code snipped out of the compiler. And most global IDs are just called vanilla globals, but some IDs that come from particular places, like a record selector, is a very special kind of ID. It's the one that picks a field out of a record, and it's quite helpful to be able to know which data type it comes from and which field number it is and so forth. So there's that's recorded here. I've got to say a bit more about data constructors in a second. And this one says, I'm one of the methods of a particular class, and it says which class they are. So again, you can see this ID points to the class, and the class contains a list of its methods, so they point to each other as well. Okay, so in effect, you can think you can partly think of these as a way of being able to rapidly navigate around the graph of these various data types to get from the class to a list of its methods, and from the method back to its class, and so forth. Okay? Right. So far, so good. So that's all these entity things. Now, so now we get to types, which is up here. This is sort of next layer. Right? The types up here is what the business of the type checker is to construct these types. Just a quick reminder that in the Haskell source syntax, the programmer will have written some types in the form of type signatures. But that's abstract syntax, that's HSSyn stuff. So HSSyn has a data type called HS type, which corresponds to programmer-written type annotations. Not to be confused with these guys, because the HSSyn types are, have rich syntax. If you write square brackets, type square brackets, that has a special constructor. So all the full abstract syntax of Haskell in there. And they might not be kind to correct and so forth, whereas this is the main internal lingua franca for GHC from here on, and it doesn't want to get tangled up with what the user can write. So HS type is not the same as type. One of the businesses of the type checker is to read and kind check those HS type things and convert them into the types that they denote. Yeah. So types are clearly rather very important for GHC, so I have a little about now. So here's what the data type looks like, and although term variables and type variables are represented by the same kind of variable, and also types and kinds are represented by the same data type, namely, which here is called type. So a kind is just a synonym for type. Right? This actually is in the FC2 branch. If you're looking at the head, you'll see there's a different data type for kinds, but in FC2 we've done the sort of lambda cube thing, so representative kinds are just more types. Now, you might have thought that since the type checker, being a Haskell type checker, has to know about types like for all a EQA double arrow, blah, 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 that it might need a data type for Haskell types, and perhaps a different data type for system F kind of types for its intermediate language. But in fact, we use the same data type for both, namely type, and simply view it in two different ways. So this same data type has two views. The type checker view, or you might think of it as the source language view, lets you look at the type of the Haskell type with constraints and implicit parameters in it. But you can look at the same data type with the core view, and it will look like for all a EK arrow int arrow, so the implicit parameter is now just an ordinary int argument. The equality class is now, it's really just a value of type EQA, which is really just a data type by now in the system F intermediate language. But they're both represented by the same data structure of types. Does that make sense? I'll try to explain how that can be in a sec, but that's it. Yeah.
So the thing representing EQ there, is that going to be a class under diagram?
Right, so here it's really a class, isn't it? And here it's really a data type, because a class at runtime, there's just a little record of values, it's just a data type. So as far as the system F was concerned, this is just a data type. So it has a kind of schizophrenic existence. So why don't we start with that exact thing by looking at the representation of types. So here is the representation of types taken from typeref. And the representation of types, you'd be happy to know, unlike HSSyn, is nice and small. Now, this is the whole thing. Here it is. It can be a type variable, and there's that tyvar thing. AppTy is just the application of two types. Like if you see M of A, where they're both type variables, that would be an AppTy. Or it can be a tycon app. So this is the way that type constructors show up in types. We could have had, along with tyvar tie, we could have had tycon tie with a single tycon and composed them with app ties. But in fact, we so often want to know what the head tycon of a binary application of tycons is that I choose this representation with the invariant that if the head of an application chain is a tycon, it always shows up as a tycon app and never as an app tie. So there are some slightly internal constraints here. You would never see a tycon app of something, some type on empty list, and then that in app tie of that and some other type. Instead, this type will just appear in this list. Does that make sense? And so the things that build types are careful to use smart constructors of types that make sure they maintain that invariant. And the invariant is our hope document.
So app.y, the head is always a type variable.
The head is always a type variable in a chain of app types, yes. Or, of course, I mean, this might be another app type, but in the end, you're going to get to a type variable. Yes, that's exactly so. Fun tie is another redundant thing, because fun tie is just a Tycon app of fun Tycon to two types. But arrows are so important, right, that we give them their own constructor all by themselves. Foralls are just what you'd expect. Notes are just a way of decorating a type with a set of its free variables. Actually hardly used, and I often fantasize about removing it, and I'd like to just remove it and see if it made the slightest difference. The idea is just being it caches the free variables, so heavily free variableized code we might say something, but I think it's hardly worth it. And pred tie is the answer to Norman's question. So, when we have a function like the one we were looking at earlier with some constraints, it looks like a fun tie with a pred tie on the left of the arrow. So this thing will be a pred tie, and this will be a pred tie in effect, right? And they'll look on the left of the arrow. So if I look at them with the type checker view, I can see those pred ties. If I look at them with the core view, then the pred tie is sort of is eliminated by the viewing function. And what are the possible preds? Well, a class predicate, which is a class applied to 0 or more types, so that's the EK. An implicit parameter, which has a name and a type, that's %x:\n. And an equality predicate, that's this new FC stuff of a, we can say, for all A, such that T of A equals S of A. So that's so this EQ pred is new in the FC book. Now these pred types can only apply, I lied. Usually they occur on the left of an arrow. And when you're looking at a type with the core view, if you look at a type with a core view, then it says, oh, class P, I've got, if you look at that under the core view function, there's actually a function, a type called core view with type arrow maybe type. And this function is in type.LHS. Maybe I should write that up just as this is kind of everything is very obscure until you understand this, so I hope I'm getting this right. Somebody who can look in type.LHS and tell me if I am. Type arrow maybe type. So this says, I would like to view this type using the core spectacles. And if the answer is nothing, that means it already is in the core, its outer level already is in core-ish form. And if I get a just, it means, oh yes, it was something like a pred type, and I've removed the source language stuff and turned it into its core view stuff. So a core view of this pred type of a class P would return a corresponding Tycon app of what? Oh, I've got a class and I need a Tycon. Ah, so for every class, there is a corresponding type constructor that is that gives that is the data type corresponding to the class. So I just briefly describe what I mean to say class CA where some operation type A to A and something else with type A to int. So GHC will make it as if you had also written I forget what you call it, colon C or something, of A equals colon C of A arrow A and A arrow int. So here it is, a data type declaration with a single constructor with two fields that correspond to the method suite.
It's the dictionary.
It's the dictionary. Now, so this is a type constructor. This guy is a type constructor, and but it's implicitly derived from this class. So, and unsurprisingly, you will be unsurprised to know that inside the class value is stored a Tycon, namely this Tycon. And inside this tycon is stored the class and so forth, so that the core view thing can just say, oh, let me get the tycon corresponding to the class from inside here, and then you can build a suitable tycon out. Does that make sense?
When does it return nothing again?
Beg pardon?
When does it return nothing?
Oh, it returns nothing if there's nothing to do at the outer level. So if it was given an app type, for example, it would say, oh, well, so, or a type variable, this core view thing would say, the core representation of the type is the same as.
So why doesn't it return the same type?
Why didn't it just return the same type? Because it means that when you're writing functions, if you're writing some functions over types, you could say this: f of t, if just t prime is warm ut, then just say f of t prime. Otherwise, now I'll do my pattern matching. This is all inside functions in type.lhs. So these functions over types often look like this.
So it's not recursive.
It's not recursive. No, it just does the outer level.
I see.
Right? So one advantage of being not recursive is that if you inline it, which GHC faithfully does, at the call site here, so this, then in effect it is as if you had written all these de-sugaring things and put it in F's definition. Right, so F turns into just a single pattern match that, in fact, that looks at some things and recurses on F and looks at other things and does the right thing, right? Rather than having to first call a recursive function to de-sugar it and then walk over it. So it's kind of single traversal process of code duplication. That makes sense. So call view and TC view correspondingly are non-recursive functions. So they're worth having a look at because they help you, the core view and TC view functions exactly tell you what it means to say this, the core view of a function, of the type checker view. It completely centralizes that decision. Okay? So, good. That's, I think that's pretty much it for types. I'm trying to represent it as types, and with using tycon apps and so forth to represent more complicated ones, and arrows, the same arrow to represent arrow kinds. And there's a bit at the bottom here that I encourage you to take a look at that describes some nomenclature that we use for classifying types. I won't go through it in detail now. But what's an unboxed type, what's a lifted type, what's an algebraic type? And I try to use these words consistently in comments elsewhere, so it's then helpful if you know the vocabulary. Okay? Right. Oh. So, this stuff about equality types and coercions, which I think I shall skip for now. These are all things which you can type in if you want to know more about. This is the FC stuff. I'd love to tell you about, but it's I want to use up all the afternoon just having fun. So I wanted to finish this business about data types in a sort of cursory fashion. I hope that my earnest hope is that by taking this top-level skirmish, you can then look at these pages in more detail, perhaps add more information or questions to them yourself. But at least you know where to start. All right. So in our passes, we got the we can go back a bit to the to our